Okay, let's go back to the optimization problem that we worked on in class. So in that situation, we said we have a rectangle, which we'll say has a width of x and a height of y, and on top of that was a semicircle. So the radius of that semicircle is going to be x over 2. We also were told that the perimeter of the rectangle plus the length of the semicircle, the circumference of the semicircle, that together those have to equal 12. Okay. So we know, therefore, that the radius of the semicircle is x over 2. The circumference of the semicircle then is going to be pi times x over 2. And so what we can set up then is that this equation, which is that 2x plus 2y, so 2x plus 2y is the the perimeter of the rectangle, plus pi x over 2, which is, again, the semicircle, that has to equal 12. We can simplify to say 2y is equal to 12 minus 2x minus pi x over 2, and therefore y is equal to 6 minus x minus pi x over 4. So we've used this constraint to express one of our two variables in terms of the other. And that's going to be a common feature of the problems. We set up the constraint equation, and then we solve it for one variable in terms of another. What that enables us to do then is to go to the equation that we are going to maximize or minimize, which in this case is the area of the figure. We're going to be able to substitute in for either x or y, and then take the derivative, set it equal to 0, and therefore find the maximum or minimum, in this case maximum area. So the area of the figure A is going to be the area of the rectangle, which is x times y, plus the area of the semicircle, which is pi times the radius squared, so that's x over 2 squared, and then that divided by 2 because we're dealing with a semicircle here. So that's going to give us xy plus pi x squared over 8. So when we square this up here, we get x squared over 4, and then when we divide by 2 again, we end up with pi x squared over 8. Okay, so now we sub in for y in the area formula. So we replace y with 6 minus x minus pi x over 4, which came from this equation up here, our constraint equation. And then we simplify, we end up with 6x minus x squared minus pi x squared over 4 plus pi x squared over 8. These two last terms combine to give us a negative pi x squared over 8. So we know then this is going to be equal to our area. So the next thing we do is to maximize the area, we take its derivative and set it equal to 0. So again, our area is 6x minus x squared minus pi x squared over 8. Our derivative is 6 minus 2x minus 2 pi x over 8, which simplifies to pi x over 4. We set this equal to 0 and solve, so we set 6 equal to 2x plus pi x over 4. When we factor out the x here, we're going to divide both sides by 2 plus pi over 4, and that gives us our value of x, and that's approximately equal to 2.154 meters. And so that's going to be the area, the value of x that gives us our maximum area. And what we can see here is that this figure right here, this orange graph, shows us as we change the value of x, what happens to the area of our figure. And what we can see is that we reach a peak area right around here at, turns out to be around, x is equal to around 2.17. Our y is going to be equal to, actually that's not correct for y, y is a little above 2, and our area then turns out to be 6.46 approximately. And this figure is more or less a square, giving us our maximum area.